So welcome back, and today we will be learning about moving iron instruments. So in the last few classes, we were seeing permanent magnet moving coil meters, both ammeters and voltmeters, and finally we have seen that the relation between deflection theta and current was linear. That is, theta is directly proportional to I. So the meaning of linear relationship is that the scale of the meter, ammeter or voltmeter, will be uniform. What is the meaning of scale of the meter being uniform? That is, the spacings between every point is the same. That is, on the scale, you can easily, the spacing between 2 points are the same. That is the meaning of uniform, and that's a good advantage also. That is because theta and I were having a linear relationship. Okay. Now coming back to moving iron, another class of instrument, that is moving iron. There in MC, the current carrying coil was moving between a pair of permanent magnet. But here, the current carrying coil is stationary and an iron piece is moving. Once again, here the current carrying coil is stationary and a piece of iron is moving. Okay, that is why it is having a name called moving iron. Okay, now we will just go through the derivation of that is moving iron type. Now we here also we go with some energy relationship, that is see, when current flows through the stationary coil, when there is an increment of current, then there will be a small deflection d theta. When there is a small increment in current, there is a small deflection d theta. And while there is a small deflection in d theta, then you can tell that there is a torque produced. There is a deflection torque, that is Td. So you can write the mechanical work done as Td dot d theta. Okay. Remember, when there is a small increment in current, there is a small deflection d theta, and that is actually due to the deflection torque Td. Hence, the mechanical work done is equal to Td dot d theta. Td d theta. Now, when there is a small increment in current, that is, initially the current was I, initially the inductance was L, and initially the deflection was theta. We are actually doing it in the most general way. If there is an increase in current by di, that is, from I there is an increase in current by di, then there is a deflection from theta by d theta, then there is a change in inductance from L to dl. In order to effect an increment di, see, current will increase only when there is an increase in potential difference or voltage. Okay, so to increase current from I to di, there should be some increase in voltage. And what is the increase in applied voltage? Increase in applied voltage is nothing but E is equal to d by dt of Li. Okay, we are very familiar with this equation, and we have taken L outside in fundamentals of AC, because L was considered as constant, but here L is not at all a constant. Okay, so E is equal to d by dt of Li, that is I into dl by dt plus L into di by dt. Okay, expanding. Okay, since L is not a constant, L is a variable. Okay, why L is variable? Because when there is an increase in current, the magnetic field changes. Since the magnetic field changes, inductance also changes. Okay, so when there is an increase in current, there is a change in energy balance. That is why inductance is not a constant. Okay, now what is energy supplied? See, to this equation, if I multiply throughout by I, to this equation, if I multiply both sides by I dt. So I dt here plus I dt here. So in that case, dt gets cancelled, and what I get is E I dt is equal to I square dl plus I L di. Okay, so this is what I get. Now, initially this was my stored energy, half Li square was my stored energy. And what is the change in what is the present stored energy? Since when there is an increment in current di, that is, when there is an increment in current di, I becomes I plus di the whole square plus there is an increment in inductance, that is L plus dN. Okay, so what is the change in stored energy? Change in stored energy is this complete quantity minus this quantity. Okay, I expand this thing, that is half I square plus 2I di plus di square multiplied by L plus dL equal minus half I square L. This is the difference. This whole quantity minus this quantity is the energy stored, or the change in energy. Okay, now I open this bracket. When I open this bracket, what happens? That is L half I square L, that is okay, plus 2 gets cancelled, I dl L, okay, I dl L plus half di square L. That is the first grouping. Okay, so this term will stay, that is half I square L will stay, plus I di L also will stay. What about the next term, that is half di square L? Here di itself is very small, so the square of a small quantity becomes even smaller. Take the case of 0.5. 0.5 square is 0.25. So 0.25 is lesser than 0.5. So di itself is smaller. So taking the square of di will become even smaller. Okay. So we can neglect such terms. So this term will be neglected. Then opening again. So this one is half I square dl, that is okay, plus again 2 and 2 gets cancelled, I di dl. So again you can see that a smaller quantity is being multiplied with dl. So again that quantity will be neglected, and one more thing, again this term also will be neglected because half di square dl, this is a negligibly small quantity. Okay, so all higher order terms are neglected. After that we'll get this quantity, that is I di plus I L di plus half I square dl will be the change in energy stored. Okay, now from the principle of conservation of energy, we can tell that electrical energy supplied equal to increase in stored energy plus mechanical work done. So electrical energy supplied we have derived in the first case, that is half I square dl plus I L di equal to equal to this one, that is energy stored, this whole thing plus the mechanical work done. Okay, one thing is that is this term and this term are the same, they get cancelled, and remaining will be this one, that is I square dl equal to half I square dl plus td d theta. Okay, and this thing is also I can bring this term to this side. So what I get is half I square dl equal to t d theta. Okay, when I bring this term to this side, I'll get half I square dl, then the remaining only this term, that is equal to t d theta. From there td is equal to half I square dl by d theta. Okay, so here you can tell that, okay, coming to that, okay, so this is the equation of deflecting torque, and here also we prefer a spring control system for providing the controlling torque, and we know that spring controlling torque Tc is equal to k theta, where k is the spring constant. Okay, now at the steady state deflection point, or at the equilibrium or the final steady state position, deflecting torque should be equal to controlling torque. That means k theta should be equal to half I square dl by d theta. Okay, now from here deflection theta equals half I square by k dl by d theta. So here you can tell that, here by seeing this equation you can confirm that theta is not having a linear relationship with current. Theta is not having a linear relationship with current. Instead it is having a square relationship. The equation is following a square law. Okay, that is theta is more or less proportional to I square. Okay, see, I cannot ready-made say that theta is directly proportional to I square, since half is a constant, since dl by d theta is not a constant. Okay, because as current varies, L varies, theta also varies, so dl by d theta is no longer a constant quantity here. Okay, so that is the greatest disadvantage of this meter. There in MC it was having a direct relationship, so scale was uniform. Here it is here the equation follows a square law, so the scale will not be uniform. Okay, so there are two types, that is two types of meters, that is attraction type and repulsion type. I'll explain using figures. Okay, so first we'll see the uh, attraction type. Sorry, so where is the attraction type? Attraction type here. So okay, this is the attraction type meter, where we have the coil here. This is the stationary coil, and in between we have an iron piece, which can move. Okay, so when current, so this iron piece is attached with the pointer, and the whole system is attached to a piston. Okay, and the piston is actually uh, is attached to an air chamber, so that will provide the damping. Okay, so spring control is used for controlling torque, and an air chamber damping arrangement will provide the damping torque. So what happens when current passes through the stationary coil? It will have its own magnetic field. So when it gets magnetized, this iron piece obviously get attracted. Okay, so the iron piece will move from weaker magnetic field towards the stronger magnetic field, and that is why it is called attractive type moving iron instrument. So here the iron piece is simply moving, it is attached to a pointer, and the whole system is attached to the pivot or a piston, which is connected to the chamber. Okay, so when the current flows through the stationary coil, the iron piece naturally get attracted towards the stronger magnetic field, or towards a path of lower reluctance. So what happens? So the pointer moves over the graduated scale, and we'll get a reading proportional to the current flowing through the stationary coil. So that is the working of an attractive type instrument. Okay, now the next type is the repulsion type. Here it was an attraction type. Why it was called an attraction type? Simply the moving iron piece was getting attracted towards the magnetic field, which is caused by the current flowing through the stationary coil. Now coming to the repulsion type, you have two types of repulsion type meters. One is a radial type and other is a coaxial type. First we'll see the radial type. Here we have again the stationary coil which carries the current, and we have two vanes placed between the magnetic field. One is fixed and the other is moving. So movable plate is actually fixed to the pivot, which carries a pointer. So what happens when current is flowing through the stationary coil? The two vanes will get similarly magnetized. Similarly magnetized in the sense, one will similarly magnetized when they get similarly magnetized, they get repelled. Okay, the repulsive force will be there. Okay, so when repulsive force will be there, the vane which can move will repel from the fixed vane. Okay, so thus the deflection is occurred, and that deflection will be shown by the pointer which runs over a graduated scale. So this is the top view. Okay, this is the top view where we have, this is the coil, stationary coil which carries the current, and there we have two similarly placed two vanes. One is fixed and other is moving. Since they are similarly magnetized, they get repelled, and when they get repelled, this moving vane moves and the pointer moves over the graduated scale. Okay, and the other is the coaxial type. Okay, this is actually a complete drum type, a cylinder type. That is why it is called a coaxial type, and the vane is also a semicircle. Okay, so here also we have a fixed vane which also forms a part of the circle. Okay, and we have another movable vane here. When current flows through the stationary coil, the movable vane will move, and since that is attached to the pointer will run over the graduated scale, and the reading will be provided. And this spring is actually to provide the controlling torque, and that is how these instruments work. So we have discussed the general equation of an MI instrument, which is based on energy equations, and we have discussed the two types of MI instruments, that is attractive type and repulsion type. Okay, so and in the next class we'll see how can we make the scale more or less uniform in an MI instrument. Okay, thank you.